Welcome to this video on rectifiers and power supplies. In this video, first of all, we're going to talk about what a rectifier is and what it means to rectify an AC waveform. And then we're going to apply this idea of rectifiers to a four-stage power supply. So first of all, let's look at the rectifier. And on the screen here, I have two examples of rectifiers. And the first of which is what we call a half-wave rectifier. And on the right hand side we have a full wave rectifier. So first of all, we're going to look at the difference between these two types of rectifier. The idea of a rectifier is to take an AC waveform, which is an alternating current, it's positive and negative throughout the cycle, and make it so that it's always positive. So let's have a look at a quick example here. Let's say we have an AC waveform, like the one in the bottom left here. If we imagine that this waveform is produced by this AC voltage source here, we can see that this power supply is connected to a diode. Now we know that the function of a diode is only to allow current to flow in one direction, but here we have an alternating current. So initially the current will flow in one direction around the circuit, and then the current will look to flow the other direction around the circuit. Well, our diode is not going to permit a current that flows in the opposite direction. And so what we'll see is a waveform produced that looks something like this. As you can see, I've still got the positive elements of the waveform, but where the waveform was negative has been lost. So you can imagine that we've lost these negative half cycles of the waveform. This presents some disadvantages though, because by simply chopping off these bottom halves of the waveform, we've lost a lot of the potential energy that this circuit could provide. We've made these big gaps that appear in the waveform as well. So it makes the resulting waveform more of a pulse of voltages with gaps in between them. So the way to address this is to have a look at the right hand side where we have a full wave rectifier, and this particular arrangement of diodes is what's called a bridge rectifier. So first of all, let's imagine that current flows in this direction to begin with, and you can see that when we approach the bridge rectifier there's only one possible path for the current to flow. We can flow this way through the diode, but we're not allowed to flow through this diode because it's in reverse bias. So we end up at this point here. Let's imagine now the current flows in a different direction and flows this way through the diode that's in forward bias. We can't go through the diode in reverse bias, so we end up at the same point here. And so what we find is that regardless of which way the current is going in the bridge rectifier, we always end up with a consistent polarity on the output. In this case, we can imagine having a positive and a negative. The advantage of this is that we end up with a waveform like the one below. And what you can see here is, rather than have these gaps in the waveform, where we've simply just chopped off the negative half cycle, we've actually, in essence, converted the negative half cycle into another positive half cycle. And so, whereas the waveform would have previously dipped down into the negative half cycle, we've actually turned that negative half cycle into a positive half cycle. And the advantage of this now is that we're actually making use of the full waveform. The other advantage is also that we don't have these big gaps that we had in the half-wave rectifier. The waveform is still pulsing, but it's a lot more consistent than the half-wave rectifier in the case of the full-wave rectifier. Finally, let's look at the four-stage power supply. And you can see that the bridge rectifier makes up part of this four-stage power supply. First of all, what do we mean by a power supply in this instance? Well, a common example might be something like a phone charger. When we charge our phone, we plug into the mains, which has a large AC voltage, but the output of the charger is hopefully a very low voltage, something that's safe to charge the phone, and it's also a DC voltage rather than an AC one. So to convert from quite a large AC voltage to quite a small DC voltage, we have to go through these 4 stages. Modern power supplies are a lot more complicated, but I've simplified this diagram here so that we can see the basics. To begin with, we have a transformer. In some of our other videos, we look at the transformer and how it works in more detail. But the idea is that we can convert larger AC voltages to smaller AC voltages by using 2 sets of coils. Then, like we mentioned before, we have our bridge rectifier, which can convert an AC waveform into something that's always positive rather than positive and negative half cycles. Then we have a capacitor, and this capacitor's job is for smoothing. We saw the result of the full wave rectifier was still a very sort of pulsing, bumpy sort of waveform, which wouldn't be suitable for something like a phone charger, where we want a nice consistent and smooth DC voltage. So the smoothing capacitor's job is to try and literally smooth that signal out to make it less bumpy, as it were. Finally, the smoothing capacitor doesn't do a perfect job, unfortunately. We're left with something called ripple, which is still tiny fluctuations in the signal. So the last stage is the rectifier, and in this case I'm using a Zener diode as a rectifier. The Zener diode has a unique property in that it can cap the voltage or regulate the voltage when it's placed in reverse bias. So in this case, let's say that we would like a 5 volt output here for our power supply. By using a 5 volt Zener diode, it means that the voltage can never exceed 5 volts across this diode. The diode regulates the voltage to make sure that that voltage is consistent. Let's put all these stages together in a diagram which shows how the waveform changes as it goes through these 4 stages. So on the screen here I have 5 columns. The first column represents the input, and then I have my 4 stages that follow: the transformer, the rectifier, smoothing, and finally the regulator. If we think of the example of the phone charger again, the input is mains voltage, quite a large voltage, and this is not a particularly good diagram, or not to scale anyway, but I've tried to represent that here by having my waveform as being quite tall. It has a big amplitude for quite a large voltage. And we said that the first stage was the transformer, and the transformer's job is to step down or reduce that voltage so that it's smaller. So there's my step down voltage now. And next, this step down voltage passes through the rectifier. And what we said was that the rectifier's job, if it's a full wave rectifier, is to preserve the full waveform, but simply to convert negative half cycles into positive half cycles. Next, we have the smoothing stage. And because the smoothing stage consists of a capacitor, or potentially several capacitors, these capacitors store their own charge. And so even when the supply drops down to 0, as it keeps doing in our example, you can see here that my voltage keeps returning to 0, the capacitor's own charge can kind of plug the gaps, as it were, and smooth this signal out. So you can see there the capacitor's gone some way to improving this signal and making it so that it's almost a perfectly consistent and smooth DC output. The final stage is the regulator. And like we said, the regulator's job is simply to cap the voltage at a certain value. And so by finally implementing the regulator, we can remove the ripple that remains in the signal, even after the smoothing stage. And so finally, we're left with a perfectly smooth DC output. So I hope you found this video useful. First of all, at looking at rectifiers and how we can convert an AC waveform into a DC waveform. And then finally, how we can apply that in the context of power supplies, putting together these 4 stages in order to convert a large AC waveform into a perfectly smooth DC output.